Okay, we are back live. Mainly just going to be trying to get GPU drive to be what we'd like it to be. Let's see. Oh, looks good. Uh-huh. And, ooh, very spiky. Very spiky indeed. Oh, that's because of the resample, though. Okay. I think it should be good enough by 200 mil, hopefully. We will see. But yeah, this is just because of resample. It's like every 5 mil or something, probably. Let's see. I am waiting at the moment to see if we're gonna have any meeting with NYU folks. But in the meantime, I'll be here streaming. And it's gonna take a little while for this model to finish training. I think what to do in the meanwhile. I have this training locally, though I guess I could try to get let's take a quick look at some of our hyperparam stuff in the meanwhile, maybe. That'll be good. So we've got all this hyperparam work I've been trying to do. And I think we have Connect 4 maybe done by now. Let's see. Oh, tags. No, only 51 experiments. I mean, it's solved. It's solved in 200 mil. Something's weird with that. Hold on. Because if we look at cost, it's jumped to very high cost very quickly. Do Pareto run on this? Yeah, no, this is not, it's interesting that it's pushed the cost up that high. It probably shouldn't have done that. Oh, you know what it is? It's that it knows that it has a good predictive model of cost because it knows that it's going to just solve it. Didn't think about that. We kind of don't bias to lower cost, do we, if you think? No, wait, we do. We bias to highest performance. We don't really bias away from cost, really. Except in terms of confidence, I suppose. Well, that's an improvement that can be made on the algorithm, I suppose. I'm not going to mess with it at the moment because it's already very good. I mean, look, it has the hyperparams here, and we got this one is very nice. I would have liked to have seen this more in this area here, maybe. But yeah, that's a little bit of a quirk. If it has too good of a predictive model, it kind of just gets stuck. Yeah, it's pushed gamma up to max. Oh. Is there any point in leaving this? I guess there is, because it might try to... Let's see if it tries to push cost down on its own. I mean, technically, it will resample Pareto points, but I don't think it's going to search around the resampled Pareto points on its own. Oh yeah, look, it's pushed num-m's all the way to the bottom. Okay. So, there's a big improvement over carbs, but not quite the God algorithm yet. Missing a few things. I mean, we could try to think about that in the meanwhile. We could go through the carbs math a little bit and see if we can figure out how to do this. I mean, I guess I'm going to kind of keep this as a puzzle over the next few weeks to see if I can crack this. So here's the math. Let's move this to review. All right, so we got these Gaussian processes. This was originally preventing you from choosing hyperparameters too far away from your current set of hyperparameters. That doesn't really do anything for me. So we got rid of that. We replaced this with a conservative estimate of absolute performance. So we've replaced it specifically with GPY, which is a Gaussian process that takes in the hyperparameters you've chosen and estimates how well it thinks they're going to do. And we've subtracted the variance of that, or the standard deviation of that, to get a conservative estimate of the performance. So this is a local estimate. How well do you think you're going to improve over the current? And then we have this term. Not this term. We replaced this with the absolute improvement estimate. Now, because the absolute estimate is conservative, you get penalized for trying to explore regions for which the model doesn't have any support. So for which you're likely to, you get penalized for exploring unconfident regions. But we don't actually factor in cost explicitly. It's just that those two things are correlated. So in fact, if you have an accurate predictive model of performance, then you're going to get pushed to explore higher and higher cost solutions. No, you're going to get pushed to higher and higher performance solutions, which may or may not be higher cost. But there's no term that's trying to pull you towards a lower cost, right? So that's a bit of a problem. Because there's a little bit of a balance to this thing, right? You know, you don't want to not explore high cost stuff when it's needed. But you also want to try to find the most efficient solution. What can we do mathematically to represent that? We have estimates of cost. We have estimates of performance. How do we mathematically express that we want the highest performing, lowest cost solution? We can simplify a little bit in the sense that some environments, we can just solve the environment. And in that case, there is a hard cap on the score. It's a little tricky because all the scores have different magnitudes. So there's no way for us to express, how much score we're willing to trade for a faster solution. I mean, okay, one version of this is just that we want to explore the entire Pareto front, right? Well, let's think about that. This term is evenly weighted across the Pareto front. This term is likely going to be biased towards the higher cost regions. Not this term, the one that we replaced this term with. What happens if instead of multiplying the two terms, we just do one half the time and the other half the time? So one of these will be evenly sampled on the Pareto front, and the other is absolute highest performance. That still doesn't really capture what I want. You know, the best hyperparameter algorithm should be able to view its experiments as a budget, right? It's spending a specific amount of compute to run each experiment, and it should be trying to maximize the results over the entire sweep. But when we say maximize the results, we don't just mean find the absolute highest performing point, right? That's always going to be, almost always going to be the most expensive point. We really do want the entire Pareto front. You know, this term here, or the absolute term, pushes you towards higher cost. It pushes you to higher cost slowly, conservatively, but that's what it does. I mean, one half the time, the other half the time isn't bad. There should be some mathematical formalism that allows you to formulate your, like, you want to be able to formulate your experiments as a budget. Oh, let's ask Claude. I don't think that I'm missing anything obvious. I don't no math, there's no specific math that comes to mind here. But let me see if I can formalize this. So, suppose have access. Welcome, YouTube folks. We're just doing a little bit of stuff on NeoCarbs, the new hyperparam sweep algorithm, while I'm waiting for this GPU driving sim experiment to finish up here. I'm trying to reformulate this a little bit. And I think that there's some math that might exist for this, what I'm trying to do, but it doesn't come to mind. I'm trying to see if I can find a reference. Is your goal to discover the Pareto front? Or is your goal to discover a specific set of parameters? Your goal is probably to discover the Pareto front. And the reason for this is that you don't know the shape of the Pareto front, right? Very often the Pareto front is very sharp. So you just pick the corner point, right? But it could be sort of smoother, in which case you can kind of get the parameters you want for your cost and do a lot of analysis there. Pareto front. Let's see if there's anything obvious that I've missed. I don't think there's anything like super obvious, like, oh, just use, this specific model. Welcome, YouTube folks. That's kind of cool. Viewership is kind of gone nicely back up. I'm going to try to be streaming a lot more now. I got a small trip lined up for next week. But other than that, I'm pretty much just streaming all my dev and all the research. So let me see what this is. So acquisition function divided by the compute cost of evaluation. See, that's not a good function, I don't think. Wait, hold on. It's estimated. Wait. Estimated improvement divided by cost. Have I tried that one? Local improvement over cost. Okay, so the thing that's tricky here is that this is improvement over your model of cost. This is not actual improvement over your existing hyperparameters. So I got stuck on this before because if you replace this with like improvement over your existing hyperparameters, you just keep shifting up to higher and higher compute, and that kind of just goes on forever. But you know what we could do? What if we used, instead of using your existing Pareto point, what if we did nearest neighbor? How about we use the Pareto point of the next highest cost? Then what would that do? That would give you that's pretty darn good. Hang on. for any point wait, let me see. Did this actually just do it? Hold on. Estimate cost. I don't think this is quite good. It weights cost by the estimated the cost at a specific point, regardless whether it is ordered. Yeah. The other thing we could do is we could use a conservative estimate of cost. Cost minus cost variance. No, that's bad because that gives you... If you do cost plus cost variance, that's even worse. That just pushes you away from high cost regions. So yeah, this plus here, this is just going to push you very far away from high cost, I think. Let me see if I can develop this a little bit more. Oops, let me move this so I can see the chat as well. And how far are we on this? Okay, 26 minutes. I can probably even evaluate... What the Oh, it's just doing the... it's fine. It's a noisy estimate. That's fine. So... So the problem with using the estimate, right? These are both scoring functions. They're not generative. So this doesn't actually tell you the optimal hyperparameters at a specific point. For a specific cost. That would be really cool. But that would just give you like a single estimate, maybe? Can you have a Gaussian process on multiple variables? Multi-output. Involving slightly, Interesting. The reason for the Gaussian process is that they give you this nice estimate of variance. I don't know if this is a good idea. Log variances. I don't know if this is a good idea, to be honest. Hmm. 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 This is too big of a change to be exploring at the moment, I think. I think the other thing I was on was better. So let me go back and just finally formalize this. So the goal is that a key problem with carbs is it develops a model of the Pareto front, but it's not really incentivized to actually like fill in the model of the Pareto front to check it properly, because you have basically these two competing Gaussian processes where one says how good can you do with a set of hyperparameters, and the other says what's the best you could do with any set of hyperparameters. And the only time you really sample stuff is when you think that you can do better than your best set of hyperparameters, right? The best set of hyperparameters. But basically, if you have a optimal prediction of hyperparameters, well, actually, let me think. If you have an optimal set of hyperparameters, then this term, where is it? Then this term goes to 0, so ignore p-search, we got rid of that. This term goes to 0, and you sample uniformly across the Pareto front, which is actually good. That's what you want. So you're incentivized to make progress evenly across the Pareto front, really. We already tried making this estimate conservative, and it was worse. I like the idea of a conservative estimate because it kind of it means that your experiments, you're gonna make them where you're very confident that you can improve. But the thing is that hampers your exploration. Hampers your exploration because you don't go to new regions. You kind of stick too close to existing hyperparameters. And then we got the absolute term, which pushes you towards regions of high performance as your predictive model gets better. And we're multiplying those two. So the problem with multiplying those two terms is that you do get pushed to regions of higher cost as soon as your predictive model gets good. But you don't just want regions of higher cost, you really want to fill in the entire Pareto front. And also, this doesn't fill in the Pareto front, right? This only fills in where you think you can improve over the Pareto front. So if you have no samples in a region, but you think you've modeled it well, and then you don't sample there ever. Okay, so there are two separate things I'm thinking about here. One is breaking this into a conditional. So instead of multiplying these two terms and always biasing you towards the high end of cost, you could do a local improvement for some samples, and you could do the global improvement for others. So every time you take a global sample, right, that's going to push the maximum cost up for most environments, which then gives you more things to sample with the local function. But since it's conservative, it's not going to really push the cost up until the predictive model of cost gets to be, or of performance gets to be pretty good. So it's still rather conservative, and it kind of balances pushing up the cost with flushing out the rest of the Pareto front. If I modify the first term, and what the first term needs to do, I think, the problem with this is that it is right here. It is the improvement over your model of performance. It's not your improvement over actual data. So basically, you're drawing a line in and you're trying to make sure that you're very confident about this line, but you don't actually fill in the points on the line. So let me show you what this looks like in on real data. So right here we have score, but if we look at the Pareto front for this, you see how there's this big gap right here and here? It's pretty darn confident that, this is 0.91 and this is 0.99, and it's going to be about a line, from here to here. So it really doesn't feel obligated to actually run the experiments to fill the data in. And that's not great, because that means we actually don't know what hyperparameters are here. I guess technically we do have the Gaussian process. So we could just assume the Gaussian process is good, and we could fill in the whole front just based on whatever the Gaussian process comes up with. That's an interesting take. Oh, actually, you know what we should totally do? We should totally do this. We should do analysis on the Gaussian process of the hyperparameter space as it's modeled it, and we should account for errors. That's going to be a lot of nice analysis, actually. That's a pretty darn nice project, come to think of it. So we'll look into that later. But separately, if I want to actually have if I actually want the whole Pareto front to be filled in, do I want the whole Pareto front filled in? I guess in my mind, I'm pretty confident that it can do this faster. Why am I confident that it can do this faster? Do I have any reason to think it should be able to do this faster? It's freaking Connect 4, it shouldn't be that hard. Well, I can just see that it's really stopped exploring here. So the predictive models aren't going to be that good, so I'm not very confident in this Pareto front, essentially. And basically, it's giving itself repeated training data. Okay, so I see why I see why my intuition is that this is bad. Yes, you do want to actually fill in the Pareto front. Otherwise, your predictive model will be worse, so your Pareto front will be inaccurate. Okay. So the way to do this, I think it's through this term here. So this is your estimate of how good you can possibly do at a point on the Pareto front, right? So what if instead I take if I take the next point to the right, if I take the next point to the right here, and I say how much better do you do than this point? You're never going to sample it because this point is too far away. Okay, hold on. I can do this another way. If we were actually to draw the Pareto front here, right, we can actually draw the Pareto front. It's defined just as the set of points for which you can't do both better and faster. So it's like this point here, this point, this point, this point, this point, this point, and I think that's it. So what if we were to find the what if we were to try to find a point of a specific cost? And we try to find a cost that's wherever currently the biggest gap is in the Pareto front. That's a little tricky to do. Is the current approach somewhat similar to constrained Bayesian optimization? Um, yeah, it's a Bayesian method. It is the current approach is carbs, neocarbs really. We've modified it quite substantially. It uses 3 different Gaussian processes. It's a cost-aware Bayesian search where the goal is to, well, on paper it's supposed to be a cost-aware Bayesian search. It doesn't really work that way. But the goal of the algorithm is to model the Pareto front. So your goal is to find the points for which you cannot do both higher score in faster time. So they're optimal in that sense that no point is better in both cost and time, cost and performance. So this point, this point, this point, this point, and this point are the Pareto points for this experiment so far. And the problem I'm addressing at the moment is that this algorithm likes to model the Pareto front without actually filling it in, which is not great. I'd like it to actually fill in the Pareto front because the thing is, the model is likely to be wrong if it doesn't actually fill in the front and get the feedback. Got 10 minutes to keep thinking about this before this experiment over here is done. And that's complicated though. Okay, so like, I guess what you try to do, right, is you try to generate Pareto points, and you decide if they're Pareto based on your model. So you generate a whole bunch of Pareto points around, I guess, whatever Pareto point is nearest to the gap. And then you rank them by how far away they are from an existing Pareto point in terms of cost. Trying to think of what like good synthetic test I could come up with for this. There's all sorts of stuff, sure. I think it's probably you just give it a really easy problem, right? If you, okay, let's say you have a synthetic hyperparameter test where the goal is what if the score function is literally just time spent, right? So you spend more time, you get more score. So like like most trivial possible optimization problem. And then what you do is you see how well the algorithm fills in the front of that. That's actually a really good test. Let's do test. Hold on. Oh, I need my other window for this. We might not do this right now. We might come back to this because this is done in 6 minutes. Let me just see if I can walk through what the approach would be. So you score each Pareto point based on the distance to the next quickest, or to the next quicker Pareto point. So you score each of them. So for this one, it's this distance. For this one, it's this little distance. This one, it's this distance. This distance, this distance, and this distance. Okay, and then you take the max of those. So you take this point right here. Do you want this point or this point? You probably want this point. Okay, so you score them on distance to the next point here, and the max point you exclude. So you start from this point here. You generate your samples. You're going to generate, a radius of samples like this. Let's say and then you're going to generate those samples, and you're going to use your model to estimate which of those samples you think is going to be Pareto. And then among the Pareto samples, you take the one with the highest predicted cost. Not the highest predicted cost, the closest predicted cost to this point here, which is between here and here. That's kind of a complicated thing. It's pretty easy to code that up. That's kind of a complicated roundabout thing. But it does get you this point. Right? It does get you explicitly trying to sample this point. So I guess which of these points are Pareto is the bad part here because none of them might be Pareto. Kind of tricky. We're kind of onto something here, though. I like the idea of having samples to fill in the Pareto front. I also don't like the way that carbs samples Pareto points, though. Because it samples randomly among the Pareto points, and you could have a ton of clustered Pareto points. Man, there actually, now that I'm thinking about it, there's so many details with carbs that could quite obviously be improved, even after what I've done with it. I think what we're going to have to do is we're going to have to, I mean, this is going to have to be something I put some time into. So, I got some clients to deal with, I got labs to deal with, I got a bunch of stuff to deal with for the next few days. But, sometime in the next couple of weeks, I think I'm going to just have to set aside a few days, make a really nice synthetic benchmark, and test all of these things out. Like, we want something that fills in the Pareto front, that only explores the higher cost region when it's confident that the results are going to be good. So basically, we don't want this point here shouldn't exist. This point shouldn't exist. This point shouldn't exist. We should never have expensive experiments that are bad. You can have cheap experiments that are bad, but you should never have expensive experiments that are bad. Except in environments that are like naturally very, very high variance, where the same set of hyperparameters can be good one trial, bad the next. Then it's kind of okay. Yeah, we're gonna have to try all this stuff out. I'm really optimistic here though, because I'm actually like, it's clicking. I'm seeing all the different things that you want your hyperparam algorithm to do. I'm seeing how they're really apt, just not covered at all by any existing algorithm. Um, and there, my experiment is done, so we'll go look at that. But yeah, there's going to be a lot to think about here. It's pretty exciting. It's pretty exciting. Let me see. So where's my... Okay, 95. It's about what we expect here. Goal achieved. And we're going to go eval this. Oh, 15. Okay, so this is our experiment file. And we're going to go into examples, eval config. Eval config. No, model config. I'm going to put this here and we're going to see how good this model is. So wand B, run. I'm a new user to stream, sorry. Does search radius in the paper enforce that you explore that front in a local search way, possibly avoiding diving to high-cost solutions so quickly? Yes. So to look at the paper here, they have this P search term, which keeps you close to your existing Pareto points. But this is a very, very bad way of doing this search, because you don't want to stick close to your existing points, right, for no reason. You only want to stay close to your existing Pareto points when you're not confident in your ability to explore. So what I did is I replaced this P search term with using GPY. I get an absolute estimate of performance. So what is the score that your point is going to get? And I subtract the standard deviation of that prediction. So I get a conservative estimate of absolute score. So what that will do is that will slowly push you to higher cost regions, higher performance regions, which may have higher cost, but only as you're confident in those predictions, because you get penalized by the standard deviation of the prediction. You get penalized for the lack of confidence in your prediction. So that's what I've done so far. I've done a few other changes as well. It does massively better than the original. You know, there's going to be a new algorithm. It's going to be neocarbs, and it's going to be amazing for RL, but it still needs a little bit more. You know, I'm not fully satisfied with it. It's better, to massively better. It's not perfect yet. It's got some quirks. So we're still going to work on that in between all the other stuff I'm doing. Welcome, YouTube folks. Going back and forth here between, we hit 10 viewers on stream. Awesome. Yeah, I'm going back and forth between this hyperparameter tuning stuff and then GPU Drive, NYU's GPU accelerated driving simulator, which I'm trying to massively accelerate for them so that they can run lots of cool experiments very quickly. And let's see. I've been having some trouble. 78%, man. 78. Let's run the full set at the very least. But I don't know how it gets 78. There's like this huge gap between what I'm seeing in training and what I'm seeing here. Let me say return. I mean, the curve is really volatile, to be fair. Also, are they taking account the hold on, they're penalizing me a few agents here for no reason, because this is not controlled agents per scene, is it? Oh yeah, this is controlled agent mask. Okay, no, this is correctly implemented. They're not penalizing me. And that the performance should be higher than in training if you're removing the bugged agents. $78. This is very odd. This gap is like almost entirely unexplained. I really don't know where this would come from. So I have these curves, right? And the latest curve is trained on 1,000 scenes. And you can see this is the curve here. gets up to 95%. I should edit that message. 5%. So it gets 95%, but then when I eval it on the exact same scenes, it only gets 78. It doesn't make sense to me. Let me see if there's anything else in here that would tell us what's going on. So coverage is probably in percentage. New files in batch. Okay. Unique scenarios in batch. Coverage. Okay. You can see these are all good. Metrics are good. Control density is very low. Let me see if I have their experiments to compare to. They sent me some of their experiments. Hopefully they don't mind me showing. Columbia is so slow. Okay, so here's some of their, I think we'll use this one. Yeah, this one's good. So they have in metrics, control density. Metrics. Okay, we have the same thing here, and then mean and reward, 0.89. Is this what it looks like? Mean and reward, 0.95. Yeah, it's about what it looks like. Their axis is over to here, so yeah, that's about what it looks like. Mean agent, we don't have speed logged. Everything else is logged. Episode length. Interestingly, it goes way down and then it goes back up. Our curves look the same. Curves look very similar. I wonder if they have checkpoints committed for this. Maybe they do. Hold on. Maybe they have checkpoints. I don't see artifacts logged, unfortunately. Files. Code. Oh, wait, they do have checkpoints. That's nice. I bet. Okay, so they have this 7. So if this is 5 million steps, then I want to evaluate this one, 1500. I just like okay, we got baseline. Baseline. Try this instead. Why does this... Excuse me? What's the frickin'... I just do dot, is this it? Valid load key. This should be fine. So presumably this is not curling correctly or something. Or K. Okay, so this is wrong. Can I just copy this onto the container? Oh, it's zipped? What the f... What? This is not... Oh, I see, I think. Yeah, okay, I see. That's weird. I guess that's the internal structure. I didn't know there's zips. Um, it's not mounted here, damn it. Why does this not work? This always works. This is so silly. Usually you can just curl this. I don't want to have to reset this up. So obnoxious. How do I get this onto the container? Uh, oh wait, there, I can just Docker CP it. I'm dumb. Yeah, that's stupid. I can totally just Docker CP it. Perfect. Longer than I would have liked, but oops. Okay, there we go. Evaluating this. $13. I, oh, it's loading it wrong, I'm pretty sure. Hold on. I'm loading it wrong. Puffernet code assumes discrete or multi-discrete. That will be... Well, yeah, we have to add continuous actions. You have to add more stuff to it. You... What? No idea what that means. Uh... I don't know, not a robot. Generally eat food, not oil. Not try to go about this. Well, you just add, it's like I added multi-discrete. Joseph, who is this? Welcome as well. Uh, see if this now loads. Something screwy here. Because now I can't get their models to eval. Yo, Joseph, what's up? Who is 5M? I don't know from the Twitter handle. Uh, still doesn't friggin' work. What the heck? Okay, well that... Okay, it's loading the freaking network wrong. I don't know how. Is it? I can't freaking tell. I can't get their net to eval now. Where's this? GPU drive. Getting tired here. Where's Daphne? Why are you working at 8 p.m.? Damn it. Stuck on this. Wait, I literally copied this from them, right? So there's literally no way. Hold on. I copied this from them. Buffer. Oh, wait. It's in examples. Nope, not external. Okay, so they do have 192 for hidden in here. Or 128, I mean. I don't think that fixes it. Man. What are the odds that this checkpoint actually does this poorly? I think that's close to random, though. Yeah, 14 should be close to random. Maybe they changed the architecture since uploading it and it screwed stuff up. I don't know. Maybe they got custom branches. I don't know. But this doesn't eval. Mine does at least eval. Let's go get it back. Add this. We know training logs are an optimistic estimate. Saw multiple times. May be available to meet. Let's see. Oops. Okay, they're sending me over a checkpoint. What the hell's wrong with this? Oh. Okay. Do we have answers? Using a data center from the cluster, data is slightly shuffled. Okay. I don't know what that does. You're basically evaluating on a different data set. Weird. I mean, I've got here the 78%. They were processed on a different day. Had another relevance. Don't worry about evaluating my models. We want the standard deviation to be 2%. Well, I don't understand how. Is this literally just... What? Link the curve. Don't see another metric. Link the Wanbei. This looks like their curve. To me, this looks like their curve. Like very, very closely. 98, yep. I mean, it's like very hard for me to imagine I could have messed this up somehow. Let me look their standard deviation. Where's the darn thing? Let me see. So they have... Oh, I see. Standard... Oh yeah, their standard deviation is lower. Why is their standard deviation that much lower? 0.07? Yeah, mine are a bit higher. Okay, so why the heck could that happen? Let me look at their settings. They have 500 worlds. Let me see. On worlds, K-Unique seems they got 500. Five. It's pretty close otherwise. I think I matched hypers. I resample a little less frequently.